So we've got a pretty cool algebra question here, quite step-like, I think, in what you have to do, although not quite as long as a regular step question. So you've got to find values for which this whole thing here is a perfect square, values of m, and then you've got to use that somehow to find all of these values a, p, b, d, c, and q, and so on. So okay, cool, give this problem a go if you want to. I got it from a textbook, someone sent it to me, it's the screenshot was here from this textbook. I forgot to ask what textbook it was from, so maybe that person can put in the comments where it's from if they want to. But anyway, yeah, thank you for sending it in. Let's do this one now then. So there's a few ways to do the first bit, which is finding values of m. I mean, the obvious thing to do is just expand this out and simplify, and I grouped everything up by x squared, x and constant terms, because that just feels like the natural thing to do. And then, okay, if this is a perfect square, it's going to be of the form ax plus b all squared. And what I chose to do is just expand this out really quickly to get this, and then just compare the coefficients of x squared, x, and constants. So a squared must be this, 2ab must be this, and 8 plus 2m must be that. And that's three equations with three unknowns, a, m, and b. So it feels solvable. And actually, there's a nice little way of doing it, which is if you just square this middle term, so m minus 6 all squared is m minus 12, sorry, m squared minus 12m plus 36. This squared is this. You can just substitute this a squared into here and this b squared into here, and you just end up with something in terms of m. The other way you could do it is you could consider this quadratic to be a quadratic that only has one solution, or one root, if you graph it, because of course it just has that one root at minus b over a, it's got that double root there, so therefore this whole thing must have one root as well, which means the discriminant is 0, and that would actually get you exactly this line as well once you move these two things over, because this is essentially b squared minus 4ac. So anyway, the same kind of idea. You get this, you simplify it down, you get this, you factorize, you get your two values of m. Good. So that's the first part done. We've got our two values of m, just doing a bunch of algebra. And what I decided to do here was actually figure out what quadratic thing, what thing this makes when m is these two values. So when m is minus 2, we put in minus 2 here, which actually gives us a plus 2 there. We can expand it out and simplify, and we'll get this. We can factorize out a 4 here to write it in quite a simple way. If you factorize out a 4, you get x squared minus 2x plus 1, which of course factorizes to x minus 1 all squared. And so that's going to be the thing that the perfect square that this goes to when m is minus 2. And of course this one as well. Now this is a little bit trickier because this number is not so nice, but it's not that bad. This is 18 over 9x squared minus 14 over 9x squared makes 4 over 9x squared. Then you've got minus 6 plus 14 over 9 for our x's. Minus 6 is minus 54 over 9 plus 14 is minus 40 over 9. And then 8, you can do the fractions if you want to, you get this. Factorize out 4/9, and you get this, and then this, of course, factorizes to x minus 5 all squared. Good. So those are our two things, and I'm just going to write it super clearly. And actually, this is the step that I missed when I was doing it the first time. Jay Winfield had to give me some support. Some of you will recognize that legend. So you have this thing here. If you put in m is minus 2, you get that. So let's just write that very clearly. And again, you have this thing here, and if you put in m is 14 over 9, you get this. So again, let's just write this clearly, because that's really going to help us with the second bit. Hence finds constants such that this thing is true. Now, okay, this whole thing here and this whole thing here looks kind of similar, except here you have the two quadratics being summed in some way to make some square stuff, and here you have some square stuff being summed in some way to make the quadratics. So that's kind of cool. And actually you can jump from one of these to the other by simply writing out these two equations like I have done, and then just doing this one, because these two match quite conveniently. This one take away this one. These two things will go away, because this just take away, this all goes away. This minus this is a plus, so that's going to be 18 over 9 plus 14 over 9 is 32 over 9. Lots of this thing here is going to be this thing minus this thing. But this is now looking almost exactly like this. I just need to times everything by 9, and then I need to divide everything by 32, and then simplify. I'll end up with exactly what they want, whereby c is 9 over 8, p is 1, d is minus 1 over 8, and q is 5. And those would be my constants for the first bit. And of course, to find the other constants, I'm only missing a and b now. I could multiply this up to match this one and then take away, but actually I think what it's easier to do, now that I have p and q, is I can just look at this one here, write it out again, substituting in P and Q as what I know them to be, expand these guys out, and then just compare some coefficients. So a plus b is clearly equal to 1, comparing the x squareds, and I just need to compare one more thing. 4 is equal to a plus 25b, and of course I've got a new simultaneous equation. Do this one, take away this one, we get this, divide, we get b as an eighth, and then put that back into there and you get a as 7 over 8, and we get the answer. Really cool problem there. Thank you for the person who sent that to me. Thank you as well to Jay Winfield, as I mentioned, for the support, because I got a bit lost in it, doing something overcomplicated. But yeah, thank you for watching.